So, you know, like right now I'm thinking, okay, so we want to steal Ether. And here we have a transfer, but it uses the owner address.
Oh my god, I feel almost embarrassed to share this video. This is a very weird video. It's very old. I recorded this when I was still like in my other room having a setup there. This was the Real World CTF where I was solving another smart contract challenge. It was basically another version of the Akurada Monica challenge that I covered in videos. At the time, I recorded myself live, like solving the challenges with the intention to cut this together to show you how playing a CTF feels like for me. Unfortunately, I never got around to editing those clips, and I figured I should just like do it now. So don't be weirded out that this is somewhat like old and stuff. It's still applicable, you know, Ethereum smart contracts have not really changed at all. So the challenge I show is still like super relevant, but it might be confusing to see me like without a beard and sitting in the other room. Anyway, here we go.
Maybe you remember my video from about a year ago from the Real World CTF in China. This is where I traveled with my CTF team to the finals of the Real World CTF. I made a video just generally about the competition, and then I also did a video write-up of the challenge that I worked on. It was called Akurada Monica, and it was a blockchain smart contract Ethereum challenge. This year I'm not traveling there, but my teammates are, and so now I will help them from remote. And I thought I could try to make like a CTF playing vlog, but this will probably be very boring. But before we actually start working on a challenge, let me just quickly give you the context that I'm in right now. So here's the Real World CTF website, and you can see that the finals are happening on the 7th and 8th in December in Beijing. So right now it's the 7th of December and it's 8 p.m. in Beijing. Where I'm living, it's currently 1 p.m. I slept in a little bit. So as you can see, it starts to get late in China. And so our CTF team hopefully goes to bed at some point to get some sleep before the final day. And so me and a few others from our team are now playing remote, trying to help our team on site. Ideally, we can solve maybe something overnight, but let's see, those challenges are always pretty tough. My team also sent me a couple of pictures from the CTF area. So here it looks definitely different from last year, but it looks really awesome again. Here's the Alice table, again, 5 people on site. And look, they could spy into the screen of the team here to the right. What a fancy venue again. And somebody also took the screenshot from one of the challenge description. Important note, the vulnerability used in the expected solution has been reported to MSRC, so Microsoft Security Response Center, maybe, and will be patched in February 2020. We kindly ask you to not disclose your exploit before it's patched. The target is Edge with Edge HTML, not Edge with Chromium Core. Besides visiting your exploit URL via the address bar, your exploit should not contain more than one click as a user interaction. Yeah, so, I mean, this is a challenge I have no damn clue about. By the way, is Eat Sleep Porn Repeat playing? Because they might have unfair advantage together with Flux Fingers as the team Flux Repeat. And I know at least one person that has a lot of experience with Edge. So I expect them to solve this. And here's also a screenshot from the scoreboard. And as you can see, Alice was at least at rank 1 at some point. It looks like it's a bit easier to solve some challenges this year. If you remember from the other video last year, there were a couple of teams that didn't solve even a single challenge. So I guess maybe they toned down the difficulty for the time frame a little bit. So like last year, there's another blockchain challenge, so let's check it out. My teammates in China have uploaded the file already last night. I was actually awake when the CTF started, so that was around 2 a.m., 2:30 a.m. German time. And so I already had the files last night and I had a quick look at them for like half an hour or so. But I really want to go to bed so I could be awake when our team in China has to go to bed. But I got a little bit of time last night already to look at it, so let me quickly catch you up what I already know, and then let's try to approach this. So here's the challenge description. Hi there, my agent said a smart guy solved my challenge last year, which successfully caught my attention. But that was just a starter. You won't expect to win my heart with only an appetizer, would you? This year I will be serious about the challenge, and the gaming environment will, hopefully, be more robust and player-friendly. Let me present you the next generation of smart contract proxy, Monica's tag-based proxy, Montagy. The last year's challenge was called Akurada Monica, so it's kind of like a follow-up from that. Try to solve any of the puzzles and empty the proxy balance. And then we get here some information. So we have here a Web3 HTTP provider with a unique URL for our team. So Web3 is like a API, a protocol to interact with an Ethereum blockchain. It's an API that is offered by Geth. We get the target contract address. And once the balance of the target contract is equal to 0, the backend will send flag data in a new TX. And then we get some files. We have the genesis.json file and the player private key.txt. That is kind of just important to make your private chain work, especially for debugging. The Genesis JSON block just contains a Genesis block for the blockchain, and the player private key is obviously your private key, so you can actually have an account and you can interact with the blockchain. So this Genesis JSON file is just a config file. It basically describes the Genesis block of an Ethereum blockchain, and it basically allocates already like funds to two addresses. So this is, for example, what we just learned, the contract address. So the contract has an initial balance that is defined here. I don't know what address this is, but my assumption would be that this is us, the player. And we get some balance already. So we have enough Ethereum to deploy attacking smart contracts and do transactions to play around with and all that stuff. And the player private key is just our private key. And then we get a sample Docker. So we have a local debug environment with this Docker file. So this is nice because last year the challenge server was very unreliable. And you don't need to scan any ports or look for other APIs. This is all we got, the Geth Web3 API. And there's a hint, an identical environment has been deployed on Robston. And then we also get a hint here, an identical environment has been deployed on Robston. Robston is an Ethereum test network. But this is only to help you understand the situation. Don't interact with this address during the contest. A blockchain is obviously that all the transactions are public. So if players would like solve it or test it out, what they are doing on Robston, then everybody else could see that. That's obviously why we get a private chain. But let's have a first look on Robston. So this is a contract. We can also find the contract source code on here. So I guess we should already copy that out. Let's call this montagy.sol, and yeah, let's install here some Solidity stuff. All right, now we get syntax highlighting as well. Okay, now if you know last year's challenge, you know that I don't know yet if I want to trust this code here, but let's see. So after this contract creation, we see a lot of other transactions also coming from the same account or address that was creating the contract. So we can also have a quick look at them. First transaction, it was calling register code, and this function takes bytes A as an argument. You can see it sends a lot of bytes, and I guess register code, this is probably raw Ethereum bytecode here, but let's take notes of that. The second transaction calls also register code. The beginning of the code here is almost the same, but you can see a few bytes changing here. And when you scroll down, you can also see it has a different length and the bytes here are completely different. So I guess two different Ethereum bytecodes are submitted there. We will check out what the function does in a moment. The next call is to set game. It sets a bool status, and we can see the parameter to be a 1, so a true. Next transaction, new puzzle with code. Now I would like to know if this code is the same or similar to the other codes. It seems to be very similar to the first code. Let's scroll all the way down. 59 length. Okay, so yeah, this seems to be the same code. Code A and also code A. Next transaction, new puzzle again, this time 47 long. This seems to match with the second code. Yeah, so this is code B. So let's call this code B. The next instruction calls set game again with Boolean true. And then the transaction after that calls set game again with true. All right. And then the last transaction calls set game, but this time it's all 0, so false. So like I said, I'll just quickly go over the stuff that I already looked at last night. So let's quickly have a look at the code. So this code came from Etherscan. Let's go over a quick detail that might be important. So the contract code we got from Etherscan, and it said here, submitted for verification at Etherscan.io. And the contract source code is verified. Last year, we saw a backdoor how you could modify the code. And I don't know if Etherscan would have caught that, how that was done last year. So maybe the challenge creator came up with another trick to fool us here that this is not actually the real code. I mean, the basic explanation for how this verification works is that they just compile the code with the exact compiler version, and then the byte output has to be exactly the same. But I believe it is not 100% the same. I believe that there are some fields, I think there's like a random value somewhere that might make it different every time and you ignore that part. So I wonder if the challenge creator found a way to fool us somehow. I mean, this is here just suspicion. I don't know, but you know, knowing last year's challenge, I'm a bit careful. So keep that in mind. This code here was submitted by the challenge author, and it seems to match the contract creation code that was part of this transaction. But yeah, I don't know, keep that in mind. At least this year, the constructor doesn't have nasty backdoors like last year. So very typical, we just write an owner as the sender, and then we have the game on Boolean. Then we have a couple of modifiers. These are like access control. You can see here, you can add them to certain functions and they act as kind of like access control. So this function here, set game, can only be called when this is true, and this is only true when the sender of the transaction is also the owner, which was set during the constructor. So another access control modifier we have is only puzzle. So there's a puzzle checksum dictionary or map, and the sender has to have something set there. So not null. Null is like the default point. So if there's a checksum for this puzzle, then it would be allowed. And then only game on. This Boolean game on has to be set to true. So this is important for this function set game because only the owner can change the status of the game from true or false, which we have seen in the transaction log. And it seems like the last transaction was set game to false. This means all the functions that have this modifier are probably not callable, at least right now. We would have to see if the real challenge has additional changes here. You know, you could imagine that maybe every 5 minutes it turns the game on and off again, and then maybe you can like erase it or something. Keep that in mind, but maybe not because it was like setting everything up and then locking the game. So that maybe is fine. So yes, we have set game to change the game status. Then we have register code, which takes a lot of bytes as parameter. This was the first function that was called after the contract creation. So it calls the function tag over the code that was supplied, and then sets isOfficial checksum. Okay, so we have an isOfficial checksum and we have a puzzle checksum. Let's have a quick look at tag, which looks like a very crazy function. It's here inline Ethereum assembly, but just a very quick view without knowing the details about it. I mean, it does like shifts and adds and divides, multiplications. There's like an XOR stuff. And we have here like for loops. This for loop always loops for 4 iterations, while this for loop starts at the head, goes to a tail, and has a group size of 16. So yeah, I think this just loops over the whole memory. We can also see here it returns bytes 32 CS. Now, actually, I'm not quite sure. Is this 32 bytes or are these multiple bytes that make up 32-bit? Let's quickly Google. No, okay, it seems to be the limit length of bytes. So it is 32 bytes long. So this is long. So it's called checksum, or we could also call it a hash. So it will create this checksum, a hash of the code, and then it will set the official checksum for that hash to true. Then we have new puzzle. And this was also kind of called after the register code stuff. And code can only be registered by the owner. And then we have new puzzle, which was also a function after the register code stuff. And it also uses the same checksum function of the code supplied here. And then it checks if the isOfficial checksum is set. So you can first register code, and then you can call new puzzle with the same code. And if it has the same checksum, it will pass. And then it will actually deploy this code. So the code that you are putting in is another contract, and this contract will deploy this other contract. It will, I guess, deploy a puzzle contract. And then we have here the address of this deployed contract. And we remember this newest puzzle address and last child address. And we also remember the checksum in puzzle checksum for that contract address. All right. So these were all the important functions that we have already observed. So let's check the next functions. Then we have the function solve, which can only be called when the game is on and only by puzzles. So only addresses that were registered with a puzzle checksum in here can call this function. And when this function is called, presumably when the puzzle got solved by somebody, Ether is transferred to the owner of the contract with the balance of this contract. That's kind of weird. Why would you send the Ethereum that you won from solving the puzzle to the owner? You would kind of expect that it would send the Ether to the player or whoever solved it. But anyway, I'm so suspicious of everything I'm reading here that seems a little bit out of the ordinary. We also don't know yet how this function is called, if it's like a delegate call or a regular call, which affects what, for example, address this or how the transfer works, I believe at least. So, like right now I'm thinking, okay, so we want to steal Ether. And here we have a transfer, but it uses the owner address, which was set here. So I wonder if our goal is to somehow override like the owner and then solve a puzzle and then get the money transferred. I don't know, that seems like crazy, but one of the ideas that I'm thinking about. And then we have here this internal function deploy, which was used by the new puzzle call. And it uses the create opcode. So I don't know from the top of my head if this is like the correct way to like create or deploy a contract. My initial assumption and feeling is, yeah, this is just typical setup, but let's maybe just quickly check the documentation. So this is create with 3 parameters. We create a new contract and you have to specify the start address in the current memory from starting at P with the length N, and you send Y. So code is memory, and I guess it takes an offset of hex to 0 from start of that memory. That might maybe strip away some, I don't know, I would need to look again at the exact internals, but mload. Okay, mload reads a value from memory. So it reads a value from the start of code. Okay, so it might be that, I don't remember exactly the bytecode, how a contract deployment bytecode looks like, but I would assume that the length is stored like in the start. And so you load the length from the start of the memory, but the contract actually starts at offset hex to 0. So this is the start address and you load the length from that address and you don't send any Y. So I would assume that this is fine. And then we have here just a check. If the code size of this new address turns out to be 0 for whatever reason, then we would revert this call and abort. Okay, so it's kind of notable that new puzzle can be called when the game is on by anybody, not only the owner. However, the checksum has to match. So obviously with checksums, it is if you could somehow create a collision and different code has the same checksum, then you could bypass this check. And then you could potentially deploy a new contract if the game is currently turned on. But I don't know yet what this will do. But if we assume that this would be possible, but we could definitely then control the size of the contract that we are deploying, which might be interesting. I wonder if you could, like, for example, make a larger size and then it would take more from the memory and deploy it. I don't know if there's like any interesting data in memory there. Probably not, but again, like these are kind of the side effects that I try to think about and keep track of. And then we have this last child address. Where's this used? Is this used anywhere? It's not really used here. Okay, so this is basically as far as I got last night. I just had a quick look at this, trying to roughly understand what's going on. But I guess it's very important to look at the codes that were submitted here as new puzzles and deployed. And also, I'm not really sure about only game on. It seems kind of weird. We would assume or hope that the game would be turned on. But again, maybe there's a way how you can screw with the puzzles to then do something. Oh, but there's one thing that I'm confused about, because it says here that it's a smart contract proxy. And smart contract proxies are basically, you have one smart contract that stays in place. And then when you call that smart contract, it basically executes a different contract. And this way you can kind of like update the contract. you can point it to this contract, and when you want to update, you point it to another contract. And now you still call the original proxy contract, but now it will execute different code. And so typically how this is implemented is with a fallback method. And this fallback method just basically takes the call that you had and like relays it to the other contract. But we don't have a fallback method in here, which I find weird and suspicious. Oh, and one other thing I noticed on Ropsten. So when we look at the address that created this contract, and so here are all the transactions from that account, and we can see here it created the contract, but it also got the initial ether to do all the setup from this address. And this was 17 hours ago. So a little bit before the CTF started, this was here set up on Ropsten. But then I noticed that the ether that this account got also had activity 52 days ago, which is still kind of like a little bit suspicious. And I noticed there are 2 contract creation calls here 52 days ago. So we can look at these 2 contracts. And the first contract is called Monica Bank, which might be important, which definitely seems related, right? Monica, Accorada Monica is definitely the reference. And there's also an event sent flag. And here we see functions like win, transfer balance, guess random, buy credit, withdraw credit, get Ethereum balance, and kill. So I assume this is the contract this backend service basically uses to check what happens if you win, and then essentially make this transaction to send the flag. But I wonder if we can ignore this or if this contract is somewhat important for solving this challenge. And then there's also this other contract which doesn't have code, but there are a couple of transactions on there as well. And here we see, for example, a call to this contract with 123, 123. Kind of suspicious. Very, very weird. Might just be unrelated tests and unimportant, because I would assume the challenge author is aware that you can just like go back in the transactions and see that here these setups are there. It might also be that the actual chain, the test server, or also this Docker chain contains these transactions as well. So maybe they are relevant or not, or let's say they are not actually like leaking any hints or so. But yeah, it's definitely something I noticed, and again, keep in my mind. So now I'm wondering what to do next. There are definitely 2 to-dos that I still have to do. First of all, I need to make a local Ethereum setup, like with Web3, to have like all the code and interact with it. And of course, I'm a very well prepared CTF player. So of course, I did not do this before the CTF. And so I have to do this now. And all of that I want to do on the Docker image. So we need to also set up this Docker image and see how to interact with it. And then basically we need to verify what kind of information is the same with Ropsten, and to verify if the game is actually off or if it maybe get turned on again. And when we have this set up, then we definitely should, I guess, reverse engineer these 2 puzzle codes that we saw. But before I get to do that, I actually have to take the dog out. You know, it's real world CTF. I have real world problems to take care of. Not problems, but I have to take the dog out. All right, I'm back. So I first need to do a little bit of setup stuff, because like I said, I'm a very well prepared CTF player. So I need to set everything up. Basically, I want to set up Binary Ninja again for the disassembling of the Ethereum bytecode. Basically the setup I had last year. Never really set up Python on Windows, so let's see how we can get pip. Uh-oh, I tried to install the requirements for the Ethersplay plugin. Microsoft Visual C++ 14 is required. Oh, I need a Microsoft account. What the fuck? We couldn't find any downloads for you? Please be the correct version. Build tools 14. That sounds good. Yeah, okay. Okay, while this is installing, let's go. So the second thing I need to figure out is, I have here this VM, but the problem is this Docker backup tar file is on my host machine. I hate computers. Obviously, I can't find any USB key. That's my IP address, 72. How did I set up the network for this VM? Okay, so here's the VM virtual Ethernet adapter. Let's see if we can reach it with that. Okay, there we go. Okay, so this is a tar archive. Sudo docker load. Okay. Okay, Visual Studio also seems to be installed. Let's try this again. Okay, so this should have worked. And now let's go into the preferences. On this Python installation, interval 3 is installed. It also says here it's falling back to the bundled Python. So how can we tell it to use the system Python? Now I worry that my edition here of Binary Ninja is a little bit too old to change which Python version to use. I mean, my license ran out already in 2018. I wonder if I can somehow get authentication failed. Oh man, we do have the Docker image here now. Let's see, sudo docker run that. Okay, it seems to be running. It's mining blocks, I guess, like geth and stuff. It's doing stuff. So we see it running and exposes here a couple of ports. It's still in launch chain. Let's check with that back in a moment. Oh, wait, let's maybe docker exec -it and check this script here. So in here we see, so yeah, okay, so here it starts geth, then waits 2 seconds, and then it runs deploy and watching. We need to wait until any miner has included the transaction. Wait until a certain TX is mined. Watch the balance, sending flags. Obviously the flag here is not included, or it's like just a test flag. But yeah, okay, so this is like the server setup. Maybe we could also, here we can also see it registers the first code, then it registers the second code, then it does start game, then it does new puzzle, and then new puzzle. But here, stop game is commented out. So the challenge server does not have the game disabled. I guess it was only disabled on Robston, so to prevent anybody from properly interacting on and leaking stuff on the public Robston test chain. So it would make sense if the game is still up. Yeah. And start game here, and start game here, and start game here sets here the parameter to true. So we only have here call to start game, which enables the game, but we never stop the game. It's commented out. So here the call with false is never done. Good to know. Okay, maybe we could also check if we find the Solidity source code here in the Docker container as well. Doesn't look like it. Let's check in here again how it's here deployed. Input p1 code. And so when it calls register code, it uses here input p1 code and input p2 code for the new puzzle. Okay, so the code in here is hard coded, but that's nice. So we already have here a cool way to just copy out the hex code. We also have this new server here. So what's that? Okay, so this is the game server that's being deployed. Let's see. The output of this would be server address. Let's quickly check here this output. The output would be somewhere here, server address. Here it is. The game server has been deployed to D068, which we know is the target contract address. So yeah, nice. Let's see, was there any other contract deployed before that? Here's the transaction output, submit contract creation. So let's look if we can find another one of those. No. Okay, so I wonder, I guess this Monica bank account is not part here. So I need to set up everything to work with Web3. So I installed NVM really quick. And then I use NVM to install the current stable version of Node. And then from the Docker file, how here this chain was set up, we can kind of like steal a little bit here, the setup, npm install web3. I guess we could also install this. I don't know. Let's also download the private key. I'm so close of ordering another Binary Ninja license. So like I said, I want to write some code to interact with the chain now. And so I'm just copying and pasting a little bit out of the provided deploy and watching script. Then we load the private key. Then we set the provider. So in this case, it would be, it should be localhost, and I guess like here, this kind of port. Let me actually pull up my code from Accurider Monica. Okay, so here's my code from Accurata Monica. I guess we also need Ethereum JSTX. So what did I do? How did I do this here? The HTTP provider, and then create a logger agent. Okay, now send signed transaction, send signed transaction. Okay, so at least we have here some code to send transactions, but I actually wanna, do I not have the debug script in here to logger.js get block? Oh yeah, okay. Here's my recursive ugly code. Go in here and let's see if this works. We start with block 0, and then we get the block 0, and then we show all the transactions. Should have maybe installed it in the correct place. Priv key open. Okay, it's doing something. I guess it fails to get the block. The ports are not exposed, so I guess let's stop that container again. And instead we specify that we want to expose. And then I guess we could also the current working directory as pwd wrong ticks. There we go. Okay, so let's start this container again. Okay, so this seemed to have worked. So we have block 0, block 1, block 2, block, and then we have an error. Then it's not a function. Okay, I guess maybe this code is not compatible with the Web 3 version that I used back then. So let's see how get transaction works. Get transaction should have then. It should also have a callback, so maybe we can do like this. Okay, so now it's running through. I changed this to second parameter callback and not dot then. All right, so now we are looping through all the transactions. And I guess if we like go to the start of this, so this block 157, 18, 9. So here's obviously a huge input. So here we can see, for example, this transaction has the input that starts with 81D8. And if we look in our deploy script, we see that here's this transaction where they set it up. So 81D838E5 plus the puzzle 1 code makes up this whole transaction. Okay, so now we can interact with the blockchain. So I guess now we need to reverse engineer these puzzle codes. Let's see how we do this. Am I buying a new binary ninja license? Oh, god damn it. Let's not maybe spend $150 right away. Let's see how far we can get with other decompiler and disassemblers for Ethereum bytecode. Alright, JEB also had an Ethereum smart contract decompiler, and it sounds like the demo build can be used to reversing contracts. So let's check out that free trial. By the way, what is the pricing nowadays for JEB? Still like 1K per year. And that's only Jeb Android, so it would be almost 2,000 for JEB Pro. And the problem with JEB is that it's not like Binary Ninja or IDA, where when your license expires, you can still use the tool, just like the old version that you still have. You can actually not use the tool anymore. Past expiration date, your software will continue to work and allow you to open and work existing projects, but you will not be able to create new projects. Oh, come on, this is so annoying. I need JDK or 8 or higher. Windows. Are you fucking kidding me? Everywhere I have to fucking log in. Let's see if this works. Detect Win32 support for It's a 64-bit environment. Are you kidding me? Did I accidentally install Java for 32-bit? This app can't run on your PC. To find the version for your PC, check with the software publisher. Okay, I don't know what I did, but now it works. I guess we could actually directly from Robston. That's pretty cool. So this here is definitely... Oh, wait. I didn't check that. We maybe don't need to reverse engineer this. Look here. So this contract is obviously creating other contracts. So this contract, upon a deploy, is obviously creating other contracts. And so now we just need to find the addresses of these other contracts. And so we can go here, read contract, and we know that the last child is, for example, such an address. Oh, we could also enter here some bytes to check the output of tag. Here you can see the checksum being generated. And so this here is definitely one of the contracts, 6E. And here the contract is actually deployed. The code was actually for it published here. So we don't need to decompile this. So Montagy, contract P2, public server, Monica init. Okay, so this looks like weird code. I don't really understand immediately. Like there's a public function loose, it returns true. And we have this init function that sets these values. Oh, it only returns true if these requires hold true. And we have here like a formula. So like this is, here are two numbers being generated, and then you have here certain restrictions. You can probably write a solver for this that solves these equations. So basically to figure out what A, B, C, D, E, F, G have to be to pass all these tests. So this is something we could do. I don't really know where this gets us, but oh, loose is used for harsh down here. So if we successfully called init, we call loose, then there's a seed, and the seed has to, the hash of the seed has to be equal to this. I mean, this would be guessing, like, so now let me think, how can we get the other contract? Because that one is obviously not stored in the last, because there were, this is code 2. Let's see the first code. How could we get to that? So we know that this is the last code. Maybe Robson can help us here a little bit. Oh, here are the two contract creations. So, okay, so this is the other puzzle contract. Okay, now we have both puzzle contracts. So let's maybe get them out. So puzzle 2, and then we have puzzle 1. Okay, so let's have a quick look at puzzle 1. Wait, did this also have a constructor? Oh yeah, okay, so the constructor setup is the same. So the sender, the person that deploys this contract, is then being saved as a server. So server will be the Montagy main contract that we know from earlier. That's the same. And then we have here hello, which can be called, which just would read, write, cut, flag. So would just return. And then we have day here with 0 + 0. Wait, what? And then we have demo, which takes also these parameters and performs a calculation here that has to be equal to that. And if that's the case, calc, which is the return value, is be set to true. And then we have easy with more restrictions. So the SHA-3 hash of A, binary, and SHA-3 hash of B should be equal to this. If we get past all of these, we call solver with info. So I guess we need to be able to figure out these parameters to solve these puzzles. So this is definitely something we could try to figure out. I definitely need to ask for help because I'm not really good at how to solve these kind of equations. Especially with these Keshack hashes, it might mostly be brute force. Wait, let's see, this hash. Yeah, so this is the one thing. Uh-oh, doggy wants attention. You doggy. Jockey. You're doggy. So I see two to-dos right now. First of all, it would probably make sense to kind of like formalize and extract these conditions here that need to be true to win those puzzles. So I could try to rewrite them in kind of a pseudocode that I could then give to some other people from the team that could maybe help solve that. And then the other thing that I would like to do is I would like to make a test setup where I have like my own puzzle that I can solve, because I need to understand how this server solve with the info call. This is very weird that you can control this memory info data and that you send that to this address here where you then have the transfer, especially takes the owner. I'm not quite sure here on which memory this operates. I don't know this from the top of my head how exactly here the interplay is with if you call this contract and then it calls back to this contract, and then here the owner Which owner would that be then? Can we somehow make our self-owner? On the other hand, do we really need to solve these puzzles? Is there maybe a way how we can... Is there maybe a way how we could deploy our own contract? Maybe we could also bypass this checksum. Then this would deploy our own contract. And so I need to quickly research again or figure out if we can force the deployment by this contract. Could we then take out the Ethereum from during that deploy call? Okay, yeah, I definitely want to do some dynamic testing next, I believe, to figure out what exactly the goal would be here. It's just midnight in Beijing right now, so my teammates are probably still awake, but they should get to bed soon. And for me, it's 5 p.m. already. Oh gosh, I'm so slow. And I haven't eaten anything today yet, so I guess I quickly make myself some instant crap to eat. Let's not waste any time and let's watch some YouTube while we eat.
Don't do meth.
All right, so let's do this. So I need to verify a few of the assumptions and plan a bit more. So let's use Remix. Holy crap, this changed a lot since last time I used it. Okay, all right. So let's get the Montagy source code. There we go. There's the settings. I need to change the compiler version. Wow, this really changed. I'm really confused. Debugger activate. Deploy and run transactions. We want the Solidity compiler settings. Okay, all right. Okay, so now I have this here on the side. Nice. Okay, so this was apparently 5.11. And on Etherscan, we can also see here the exact version. Do I want to make certain changes here? Yeah, I don't know. Let's compile this code. Okay, so we have here the contract code. And then we can here deploy it. So let's deploy it. And then we can add here a new puzzle. So let's create our own test puzzle. So let's make here like a P3. So we have this set up. And then I guess like instead of all of that stuff here, we just make this info call. So we can just call the server here. So let's compile this one as well. And then I guess we want to get like the code to publish this. That's a good question how this works. Let me quickly check the transactions. So we know that this is P1. So this is the first call. And down here we see the contract creation code. So we can go back to where this was created. Yeah, so this is the register code. And so we can see here's where the code starts. And then we have here two values, hex20 and 740. Now, if we look back here into the deploy code, we know that it adds 20 to the start of the code. This is where the actual code starts. So this makes sense. It then actually deploys the contract starting here. And then it loads this value here. Calling convention. No, I'm not quite sure. So here we have the P1 code in hex. So the 20, okay, so it basically starts here. So these are 3712 selected. So we have 1856 bytes. In hex, that would be 740. And so these are the 740. So this is the length. Now, what is the 20 here? I'm not quite sure about the calling convention anymore. Here it has to get the length, but I'm wondering why. Yeah, that might just be calling convention. Maybe Oh, right. I'm sorry. Oh yeah, no, this makes total sense. So hex20 is not like here, like line 2. I was just confusing myself. So hex20 is obviously 32 bytes. So this is just part of the calling convention for this function. And then this is where the code variable actually starts. And so it loads this value here with mload, which is 740. So it gets the length here. And then it moves the start of the code 32 bytes forwards. This is where it actually starts. And then it creates the contract from that. But anyway, now we know how to create the bytes parameter. So basically we want to get the contract creation code. So how do we get that? So we have it compiled. Here we get the byte code. Okay, now it worked. So this should be our code. The two parameters here. I guess it will always be 20. And then the length in hex. So this 1,500. So in hex it's 1,500 long. So divide by 2. So it's 750 bytes long. And then in hex it would be 2EE. So this is the length here. So this should be our whole data. So basically, we would now that we have deployed this, we would first call register code with the bytes. Did this work? Transact. Where do I see the output? Down here. Error encoding, invalid bytes. Well, okay, so wait, how do I need to encode this? 0x maybe before that? No, maybe in quotes. I forgot what the transact. Okay, so 0x for 1 worked. Okay, this is annoying. Invalid bytes value. Oh, it's frozen. There we go. Okay, wait, this worked, but I'm confused. Why does it call the fallback? This doesn't make any sense. Let's debug this and see if this worked. Why does it not do the debugging thing anymore, like in the code, like it used to be in Remix? Okay, I have to figure this out. Okay, got it. I'm an idiot. When I'm calling from in here, it already builds the parameters properly. I didn't have to add the 20 and the size by hand. It was automatically, obviously, encoded here with this call. I don't know what I was thinking. Anyway, okay, so this worked, but I'm still like, it bothers me that I can't like debug and go through that code here. But let's see, there should be a create instruction somewhere in here. So here's the create at 2612. So, yeah, here you can also see the call data again. So here's the function signature and then the 20 and 2E. That's just how the arguments are encoded. But this didn't quite work. It's still confusing to me that I can't debug this now nicely. But it's also like the fallback. Let's look again at the plugins here. Debug. Come on, I want to be able to walk through that. Anyway, okay, so let's assume this worked. Not quite sure. Then that's... Oh, no, it wasn't deploy. It was just register code. It was just calculating the checksum. I'm such an idiot. Okay, so now we need to, if you want to create a new puzzle, we need to enable the game. And the game is currently disabled. So let's update the game status. Now it's true. And now let's call new puzzle. Also with that bytecode. Let's call that. Oops, double 0x there. Now again. Okay, it's definitely doing something. It's hanging. So new puzzle was executed. Let's look at the debug here. Now it follows the code there. I saw it updating up there. There we go. Okay. Oh, it's in the P3 code. Wait, it recognized that this is the P3 code, the constructor. Oh, nice. This is awesome. Okay, so let's go back out. So it was executing the constructor here. Why is it now not updating anymore? This is so... Okay, so this is here where the constructor is executed. It's properly highlighting there. This code is so long because of the checksum calculation. Oh, wait. This is now saying... wait. Let's put them both into the same file. And let's compile the Montagy. Okay, so let's start this over again. Let's clear this register code. And the tab crashed. Amazing. Okay, so let's do this again. We compile Montagy. Okay, so now we called new puzzle. So let's click on debug. Now this works. Okay. And now we can properly step through. So game is on. And now we calculate the tag of the code. But yeah, I don't care about this. But we can now look at the checksum. So in here, this should be the checksum ADC 1, 2, 3, 4, 5, 6, 7, 8. The checksum is 8 bytes long, so this is definitely too much to brute force. We would definitely need to solve the checksum stuff if that would be our attack here to sneak in other code. So now we are here at the deploy. So now it should be deployed. The return of this function is an address. The address is from the deployed contract. So this should be the P3 contract. And we can also see the locals. Yeah, so here's the address. So this here is our P3 contract that we now just deployed. And otherwise it just sets here the puzzle checksum. Where's the puzzle checksum used again? Is this important for us? Only puzzle can only be called by solve. All right, okay. So now we go to the deployed contracts and we load at this address. So at this address, we load the P3 contract. Awesome. So now we can get the server. So in our P3 contract, we set the server to the person that created this contract. And so we can see here the server is this 692A, which is our Montagy. So this worked. And now we could call easy, and then we would solve this challenge. So let's provide some string info like that. I guess it's a string, so we need to do like this maybe. Okay, so this worked. So let's debug this. I'm curious what happens. So we are now in easy. Server is our other address. Okay, all right. So I'm looking for like the call. Here's the call to X code size. So here's where it probably check. This is like the typical check for calling the other contract. Wait, what was that? Oh, and here's the call. So the call has here the address. The parameters prepared on the stack for this call has here the address of our server, so the Montagy, and here the function definition, and then some other data that is passed over here. We should actually also see, it's probably in memory. Anyway, so we call now, and now we call the Montagy contract. And so we are now in the solve method. So now, who is the owner in this case? That's what I'm curious about. Require game is on. Puzzle, only the puzzle is allowed to call this. So here it checks now if there's a checksum set for this sender. These sounds are from my dog, I swear. He's sleeping right now. He has dreams. Okay, so now we passed all the checks. The puzzle was allowed to call solve. And so owner is in this case. Okay, wait, so there was this call here. I believe this is the transfer call. Why does it not show me here the value of owner? So who is owner now in this case right now? Wait, is our account actually maybe the owner? Because it would make sense. We have the Docker file with that deployed everything. So let's quickly check out the Docker container again. Is that the same private key file? The player address. Web3 get address from priv key. Private key to account. What am I doing wrong here? Okay, we have here the raw R and S values. I believe this data is already signed, so you don't have actually the private key of the user in here. Okay, so, okay, wait, I have an idea. So the owner is wrong, right? So when we are executing here, so the owner transfer is obviously transferring to the wrong address. But when we create new puzzle and deploy, it will execute, I believe, the constructor code from here. I believe we could inject here our own code execution to set the owner. Wait, so my theory that I had also a bit earlier was that when we deploy this contract, like let's assume we can fake the checksum and we deploy this contract, that we can execute some code in the context of this first contract, which means we should be able to access that contract's storage. But is that true? Let me try to research this really quick and otherwise test it out myself. Let's go back to the transaction. Okay, no, let's go back to the where we new puzzle. So let's debug this again. So here we calculate the checksum, and then we have here the deploy. So let's see here the code of this deploy. We have a jump dest into this deploy code, and then we call here create. Okay, the constructor is executed during the, okay, so in this context here, we lose all the locals, create, and then we have here this mstore call value. Here it gets the sender, the caller, and then it sload. We want a store somewhere. Okay, so here comes the store. Here it stores it to storage, and then it returns. No, okay, so this idea was stupid. This obviously does not work. This is stupid. So what is the effect of this memory info? When we call back the server, the solve, because we do control this info parameter here as well. So when that goes here to solve, then we write here the winner info. So here it should be setting the winner info, and I'm looking for the store. So here's the call for the transfer. Where's here the store? Am I blind? Here we have an mload. Ah, there's mstore. No, store. This memory info is really mysterious. Very, very weird. So somehow, I think we would need to manipulate here who the owner is. So at this point, I'm just hoping for kind of like a creative inspiration, something to try out, because right now I'm a bit clueless, to be honest. Let's maybe go over everything once again. So we cannot register code, but we might be able to deploy code as the contract if we are able to bypass the checksum check. But this also looks so crazy that I'm not so sure about this, if I'm completely honest. I wonder what this algorithm is. Let's maybe just have a quick check. We load a value, and then we only take the lower bytes. Okay, that should be fine. It is a bit suspicious that if you would actually implement something like this, you would just use cachec. Like they implemented hash function that is definitely like not crackable. So why implement this this thing here? But it has like multiple rounds, and it goes over. So it starts with S like this, and then so okay. So for each block, so this is like a block of 4 byte. So we have, okay. So we have your loop, goes over the group size, goes over 16, whatever that is, okay, all right. So it always moves 16 forward, 16 bytes only though. And then we load here 64 bytes, I believe, mload, how many bytes? So we always move 16 bytes forward, but here we load 32 bytes. Oh, okay, we load 32 bytes, but we only extract 16 bytes. Okay, so we go in 16 byte blocks, and we divide each 16 bytes block into 4 byte blocks, M1, M2, M3, M4. So we add this constant S. First we multiply. What the heck is T1? T1 is this constant here. We multiply and then subtract the first block. This constant here to it. I mean, this is a pretty scrambly hash. Could this be reversible though? Like at least this step here? Maybe we re-implement this ourselves and see if we break this. Okay, I do still think this should be breakable because like I said, you would use cachec or SHA-3 if you would actually want to prevent this. And you know, why would the author build this if it wasn't attackable? So I do believe the goal is to deploy your own contract. But even if you deploy your own contract, then we still can't transfer stuff away. Even if we could deploy our own puzzle or solve one of the other puzzles, we would call solve here that transfers the balance to the owner. So we would need to override the owner somehow, but you can only override the owner if you somehow can execute code in this context of this contract already. And if you can execute code in the context already, you could already transfer it somewhere else. Except you could somehow collide the Ethereum in itself uses also a key value store, and so you could maybe collide like the storage keys, but I don't know that you wouldn't be able to. I don't think you would be able to do that. But this memory info is also so suspicious. We don't have delegate calls here in this code. We basically only have regular calls. And only delegate call would allow you to modify the storage. Except only that the deployment, a create of a contract, when the constructor is executed, somehow you could still do nasty stuff to whoever called you and write in that storage. But I've never heard of such a one. But I've never heard about this being possible. And I feel like this is something people would have tested and should be documented if that would be possible. And I feel like I should know about this if that's possible. When D does a call on E, code runs in the context of E. So storage is E. When D does a call code on E, the code runs the context of D. Okay, so let's maybe check the bytecodes again, just to make sure we didn't overlook. Yeah, there's no call code in there. Only a call. Also, it doesn't really make sense that in a contract create you could modify the old contract storage, because the constructor, that code is designed to set up the variables in the storage already. Like that's basically all the constructor is for. So that should already execute in the new contracts storage. Yeah, proxy contracts typically use delegate call. And we also don't have the storage collision here with key value because we don't have delegate call. store takes a key and a value and simply assigns the value to the storage key. So here's the store, and it stores the info, the winner info in variable 4. So that's the key and that's the value. Let's go back to the contract creation. So this was this call here. Assign the server. And then we have here, it's the first variable 0, so it stores, but this is obviously the other storage context. When we deployed this contract for the first time, so here, then we should here set the owner. So here's the store setting the owner, and it's also obviously written to 0. Yeah, well, that makes sense, of course. I need a beer. Cheers. So maybe let's take some notes again, what we have. You notice now at this point I'm running in circles. I'm thinking about the same stuff over and over again, hoping to notice something. I talked to it now a couple of times, but I hope that maybe when I write it down, I get a better grasp of it as well. So why have custom checksum? Because Kazakh or SHA-3 would be completely strong enough. So that's why it's probably collidable. If we manage to create code that collides with a checksum that was already registered, we can deploy our own puzzle. The question is what that would give us, because either we solve P1 or P2, or our own puzzle, we could then trigger solve. But solve transfers either to the owner, so we would need to overwrite the owner. Only difference between P1. Oh, my parents are calling. Let's take another break. Beer is empty and done with my call. And I still have no clue. Let's finish these nodes. The only difference between the puzzles that are already deployed and if we could fake our own puzzle is that we could control the constructor code and easily solve the puzzle. But solving it only transfers to the owner. We didn't really look into how to solve the puzzles, but I do feel like they should be solvable. So this is not really an advantage. Controlling the constructor is special. We could have our own constructor code. The only thing I know about constructor code is that the contract is not really existent yet. So when the constructor code calls another contract that, for example, checks the size of the construct as a way to determine if the current caller is a contract or a normal account, then you could bypass this check basically. But we also don't have these kind of checks in here. I mean, we do have here this check after the contract is deployed, but we don't really care about that. Okay. So why is this check included? It could only mean that maybe we really want to make sure that this code was created, and if not, we revert. So it must be really important that you have like a proper contract that actually deployed something. Because maybe it might be easier to just have regular code, like short code, and you want to make it kind of like harder by ensuring you actually submitted code that actually deployed a contract. So I don't think puzzle 2 is really solvable. Like, you supply a cache seed and then you compare the 32 bytes of this. So this essentially has a couple of 0 bytes in the front because it stretches the 18 bytes to the 32 bytes. And I don't really know the proof of work of Ethereum, and so I thought maybe this happens to be one of the hashes that were found in mining, and maybe Ethereum uses cache 256 as well. Basically, like Bitcoin is doing it with SHA-256 hashes. And I just quickly looked up the proof of work for Ethereum again, and it's definitely not like a simple hash like this. It's like their own. It's like their own hashing kind of thing. It's not just SHA-3. So yeah, so this is kind of weird, but this looks kind of like unsolvable for me because this looks too strong. You have 8 bytes here, but they are stretched to full 32 bytes. So you have all these 0 bytes. And so these two hashes ended together need to result in this. This is basically still brute forcing A and B pretty accurately to like, no, this is also not solvable. Okay, wait, I believe puzzle 1 and 2 are completely not solvable. Yeah, these are not solvable. Read, write, CAT flag. Cat. Call and transfer. Create and transfer. CAT. Yeah, I believe puzzle 1 and 2 are not solvable right now. So let's change this. So P1 and 2 is not solvable. So the question is, why have the custom checksum? So the question is, why do we have a custom checksum? Probably because we can collide it, which means we can deploy our own puzzle, which means only then we are able to trigger solve. But solve would transfer to the owner. Own puzzle, we can control the constructor code and we can easily solve the puzzle. To be honest, I still have no clue how we could get to that. I still believe we somehow need to override the storage for owner so we can send the money to ourselves. And I don't really know yet how. Okay, so I feel like I want to re-implement this code here to kind of get a better understanding of it and maybe find a way how you can maybe craft your own checksums. I feel like maybe for this you would need a better mathematical brain and mathematical understanding to maybe realize that you have here some kind of function that you could easily like reverse or so. These XORs might destroy everything. So yeah, I'm pretty clueless right now. I would say I try to re-implement this now, I guess in Python first, and I hope that this might be usable in some way. At least that's one of the to-dos. And then the other to-do is still kind of investigate what you can do with the info that you pass in here. But this would be step 1 anyway, so let's do that. So we want to go to the register code call. Let's debug that so we can get one example output. So this is here the parameter. And then let's go here with the new puzzle, and then let's check the CS code here. So here we do the checksum, and then we should have here the CS. So this should be the checksum. Import bin ASCII. Let's do that again. So first of all, we loop over everything in 4-byte blocks. For block in range, and we do this in steps of 16 bytes. So we always move 16 bytes forward. So this would be this loop basically here. So let's also remember here these constants, T1 and T2. We have this S constant. And then we extract M1, M2, M3, M4. I guess this is taking here, now I don't know the byte order and stuff. We need to check this, but so M1 would be from block I to block I plus 4, 12 to plus 16. So I guess let's print M1, M2, M3, M4. Then this is here the first round. Bin ASCII.HEXTREE file. Let's do M1 and M4 because basically I want to know which order. So this is here the first output, and let's go to the start of this loop. So here we set T1, go into the loop, and now we are getting M1. So I guess on the stack right now we should have the values, and then FFF. So it takes back here 6, so let's step 1 forward. It takes 600080FD. 600080FD. Okay, and M4 is then 60806040. Okay, so it's reversed. So M1, M2, M3, M4. So we got that, and then we loop 4 times. And then we add this to S and end it with this. So S plus this, multiply T1 with 1x0, and this will be P1. So P1 is T1 times x10 minus M1. Now this should fail because these are raw bytes and these are integers. So we definitely need to convert these still. Int versus bytes. Okay, so import struct.unpack. So let's check the result from P1 to verify that this calculation is correct. We go in here and we are looking then for the sub instruction. Multiply and sub. So let's check the result here. 1B71, this looks definitely different. Let's see, the numbers that were used were 6080FD and 2171. So I assume maybe here the endianness is different. (1B710F) 1B710F. Okay, so now it's correct. Okay, so now we can do all the remaining calculations here. P2 is T1 plus S, P2 XOR P3, and then P1 XOR that. P1 is T2 times. These multiplications are basically just shifts. So in hex times hex 10 is also just like, you know, shifting it over. So these are just like shifts. I guess we can later rewrite this into shifts. Maybe we will notice then something else. P2 is T2 plus S, P1 XOR that. Okay, and then at the end, this should be the output. So we are shifting T1 by quite a lot, and then we XOR that with T2. So here, this is basically T1 and T2. So let's print hexlify the checksum, and oh, we have a float here. This is probably these divisions here. Is it dash dash to do like an integer division? So I guess this worked in principle, but we have a problem here. So here we get all these blocks now. So let's go all the way to the end, and then let's check what they unpack after this here. I guess they run into other memory, or somehow their loop condition stops earlier. It might just be 0 though. But but let's check. So we want to go all the way for the end. Oh, wait, we could check M4 already in there. So here this add call takes M3. And M3 is in this case, let's just go back up until this loop is done. Okay, so now we are here executing this AND. So EBDE. Okay, so the end here, it's definitely running in other stuff. This is the end. So it ends here. And then we have 0, 0, this, and this. Not quite sure where this code is coming from, but I guess we can just append this here, and then our code should run through and did the same calculation. So now we have EBDE2464. Okay, so that's all fine. Then I guess we go here. Awesome. And then we have the checksum. It's exactly the same now. All right. So now I wonder if this is just fixed other memory that will always be the same, or is this call now different? Like if I do the same call again, will this result in the same checksum? But it must, right? Because we did the register code and then the new puzzle, and in both cases, it did the same calculation. Okay, so here the CS should be calculated. So here's the S load. So here's loading. Yeah, CS is ABC. Okay, so it did calculate the same thing. Okay, so I don't really know where the data at the end is coming from. Something else in memory. Let's maybe check the memory. How does this look like? So here's the call data. So we definitely have, let's see, let's find this code in here. So here's the code. It stops at 0132. So memory call. Okay, so the call data has here zeros at the end. But let's see the full, where's the memory view here? Oh yeah, so this is memory. Okay, so 32, and then, but there's nothing in the end. Oh, it just takes, wait, does it take just, no, it doesn't take just zeros. Oh, does it maybe run into itself? Are these values here at the end in memory maybe the internal state information of P and stuff like that? So when we go into the code, so here, and let's check out the memory view now. No, it's all 0. That's so weird. Wait, let's go. I have a widescreen monitor. You can't see this here, but if I make this bar very, very big, I can maybe easily scroll around. Oh yeah, so much better. Okay. Okay, so here we are loading the memory. Here's the M load. So it loads from memory at offset I. So I is right now 370. So this is like really at the end now. Let's look in the memory. 370. No, we loaded the 0320. 43 EBDE 50B. Oh no, this is just reverted. These are these data. This is this data here. So wait, what I put here at the end, 264. Okay, so no, this was bullshit. It did it correct. I don't know. Okay, so now it's fine. I think I just did the loop condition wrong. Now, like I said, I don't really have a mathematical brain, but we could play around. So for example, we could figure out what happens if we just add some data here at the end. So we could, for example, let's say place here this as string, but we do an write fill of 064. Write just 64 with 0. Okay, so now we can like, no, we can't. What am I doing? We want 32. No, we don't. So now we have the easy ability to add easily like another block to the end. So for 1, for 1, for 1, for 1, for 2, for 2, for 2, for 2. So we added like more data to the end. And then we can see how it affects the previous output. We can see what effect does it have. So now we can make some notes. So, I mean, yeah. So this here produced this output. So let's change here a 4-1 to a 4-3, and we get this output. So we changed here one value, and we changed quite a lot of stuff. Yeah, okay, so this changes, so like it's not at least not straightforward. So what are the internals? Okay, so when you want to collide hashes or checksums, I mean, besides other fancy solution things, basically this hash loop has like an internal state with variables. If we somehow can enter data that leads to the same internal state, basically the state variables are these here. If we manage to get to the same state somehow, then we have a collision. Let's see how we can control the states. So the S state is always only written by itself. It has a start value and then always plus, 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 plus. So yeah. So I wonder, is S cycling? Let's output S here. S is in every loop the same. S always is initialized with this value, and then for all the adjusted blocks, it's always starting the same. So S is probably not our concern. And then we have T1 and T2. They start with an initial value. And T1 is written by XORing all the P's together and adding it on top of the previous T1. And T2 is exactly the same thing. It's XORing P1, P2, P3, and T2. There's one XOR stage and then there's another XOR stage. So how are P1, P2, and P3 created? They take the T1 value and subtract the block. We know when we go in here, we know the value of T1. So we can control P1. We can control P1 by the block M1 block value that we choose. So here we can definitely control what we want P1 to be. T1 plus S we cannot control directly, at least, because T1 is dependent on the previous cycles. So T1 is essentially random, but we know the T1 value. Like, we know it what it is, but we can't change it at this point. We know what it is because we can control M1, and we have to just accept what T1 is. So theoretically, we could maybe choose M1 such that when P1 is XORed with P2, these, for example, cancel out. And P3 is T1 divided by 2, 0. So let's check the effect on that. So if you have, this is in hex 1, 2, 3, 4 divided by 2, 0. Ah, shit, no, this will be something completely else. Oh, I thought it was a shift as well, but it's not. I'm an idiot. Okay, so this one is kind of ugly, but we also know T1 and we control M2. So we know the result of this calculation. I mean, this is essentially also, we know all these calculations, and we can control M1 and M2. And we can control M1 and M2 in such a way that this XOR results in something specific that we want. Let's try this. So I'm printing T1. Okay, let's try only that. So here we want to know T1, the value of T1. And then I guess we print, so here we print the XOR values. So I guess we could also, let's print all the calculations, and it's a lot more visual. So here we have T1, M2 is P3. Let's target the first iteration here of the last block. So here we have T1 times this minus our block is this value. Let's try to get this to 0. So that would basically be A, B, D, C, 7, E, F, B, C times hex 10. So we've shifted it over. We only control 4 bytes, but I guess we could like subtract, for example, this value here, and then we would only have 80 left. Okay, so we could do like that. So yeah, so we have here plus our chosen value is now A00. Then this is S, we don't control this. So this value we don't control. So let's calculate this divided by 2, 0. And now we add something to it. So this is here, this result. I guess ideally we would want this or this value here. Oh wait, we know these two will be XORed. So let's see, this here. So basically we want here now, so we XOR the lower bytes. So we only care about this. So we want to add something to here to make this value. So we can do this minus this value. So this is what we want. Wait, what did I do wrong? ADC. Now of course this calculation. I'm an idiot. Now of course this calculation has something completely else. We can't really control T1 plus S. We don't care about that. So we only care about the division. Okay, so what did we fuck up here with this division? So this here get divided by 2, 0. Oh, no, it worked. I'm an idiot. This matches. Look at this here. 7C, 7.5, these are the same now. And now we XOR all these together. XOR. Let's print the XOR result of this as well. So yeah, so this is BBB000 now. And then we add T2 to it. And we also know the value of T2. So now we and then we restrict it to FFF. So this is basically the technique that we can use when we know what T2 is, we can craft here a result for the XOR that sets the T2 to something we want. So we can control T2. And when we can control T2, we can use M3 and M4 in this calculation to do the same with T1. And basically, our goal is it to get to these values here, because when we reach these internal values, we can just take exactly this input here, and from that on out, it should then generate the same checksum again. Awesome. Okay, so we can actually automate this as well. Let's take an example Ethereum code that we want to like inject. Okay, so I guess we could do like push once. It takes you and pushes a 1-byte value onto the stack. So we could do like, if we just do 606060 as like code, we would have just like push 60, push 60, push 60. So that should be fine code. Let's call it shell code. And let's make sure that this code is at least 1 block long. So 32 bytes long. We always want this to be aligned. And basically we want to now construct a block that then gets us to these internal values. Okay, so basically we want to run the checksum over this to get the current T1 and T2. So I guess we can take this code here and create a function CS, create a function checksum that takes code, and at the end return T1, T2. Let's call this function tag like in the Ethereum contract. So we get the internal T1 and T2 state. And so now we want to construct. Let's take care of I guess T2 first. We should maybe also allow us to set here our so let's make these default values T1 default parameters, because then we can override them and we can calculate our own. We can continue calculation of the checksum. Okay, so let me think. Copy these codes quickly again. Wait, I'm stupid. Am I not? Oh no. We are looping over this 4 times. So in the first round, we can control T1 and T2 by controlling M1, M2, M3, M4. But we do this 4 times. So what actually happens then is on the next iteration, these carefully chosen M1 values will now destroy the T again. And we can't target the last iteration of these 4, because for that we need to know the T1 and T2 value in the last round. And as soon as you change the M1 and M2 to target these values change again. So if this was not an iteration, if this was just like this, then it would have been now easy, but this is killing me. Especially because I feel like mathematically you could still do it. You just have like a larger equation system and you would just need to, you have some encapsulated like formula. Yeah, okay, you know what? Let's try to write this formula in one go. We actually don't need to loop here. We could collapse this loop in one big formula, and maybe then we can, I can at least ask somebody if this is solvable now. Okay, so I guess let's create here a tag 2 where we try to optimize this, and we can then always compare. We calculate tag of shellcode and so here are the 2 executions. So we basically want this result. So basically this whole code is executed 4 times. Let's work our way backwards. So P3 is this calculation. P2 is this calculation. P1 is this calculation. And then T2 is this whole calculation. Can Z3 solve that? Still the same output. All right. Okay, so this seems to work. So let's use Z3. Let's see if we can do something with that. So we are actually just doing one round right now anyway, so we can remove that. And then we do, we import that from Z3 import. So M1 is a bit vector of size 32. So basically, the solver in the end has to check that T1 is equal to that. So this should all be fine. And then in the end, we would say solver add T1 equal to this code and T2 equal to this code. So here we get the T1 and T2 after the shell code. And then we calculate, so this makes no sense anymore. Solver check. And then we check if we can find a block, M1, M2, M3, M4, that gets us to these internal values. Unsupported format string passed. Oh, I have here still printfs in there that we don't need. I guess I could have left the loop. That was kind of unnecessary. We need to turn these into bit constants. So let's do T1 is a bit constant. T2 is a bit constant. And S as well. And then in the solver, we add T1 is equal to this. T2 is has to be equal to this. And S has to be equal to this. Okay, we can't divide. Let's see, is this supported? Solver model. There is no current model. Am I stupid? Is this unsatisfied? Unsatisfied. Let's actually make these larger to 64-bit because then the calculations are still unsatisfied. Yeah, okay, wait. This makes no sense. We need to encode these rounds here so that it's clear what is input T1, which is equal to that, and then the result T1 is different. So here these T1s, is this, I don't know if this, is this enough? Loop T1, loop T2, and in here we use loop T1, and then we assign this to input T2 like that. Still unsatisfied. Okay, I'm not so sure here. So let's print, what is T1 at this point here? Okay, T1. Okay, this kind of looks good. I expect it to be a crazy calculation like this. So T1 is this whole formula. Wait, what? This doesn't need to be bit vectors, right? Input T1, output T1, and then we remove that, and then gen block takes T1 and T2. Unsatisfied. Okay, but now it should kind of work. I don't think we need that here either. I think S equal to that was enough. Yeah, but unsatisfied. Very weird. Let me try something else. So this is T1 in iteration in loop 1 and T2 in loop. So this is both in loop 1. and then we come, and then we take here the T1 from loop 1. So all of these will be the second loop. The output is T4, and then we are checking here. Oh no, I had T1 equal and T1 equal that. Of course it's unsatisfied. Oh my god, I'm such an idiot. But anyway, it should work now. It's probably a big formula that takes a bit. I wonder how fast it will be. But let's, I guess we can now print the model solver too. Satisfied. We found M1, M2, M3, M4. Nice. Okay. So this is fast enough. That's fine with me. So now we can actually, let's take these values. How do we get them out of there? I forgot how to get the values now. I guess we can do this by hand as well. I don't care. So theoretically now, if we now generate the checksum of the code, but we start, if we basically now append the shellcode to the code and generate shellcode plus, but in the middle we place, so this was stupid anyway, gen block code, we don't use that here. Okay, so now model is equal to that, and then we can return the model M1, model M2, model M3, model M4, M1, M2, M3, M4. And then now we need to sync, let's call it a sync block, because we are syncing here the state of the checksum. So struct dot, are these integer? I don't know exactly what I'm getting out of here. So let's maybe print one of these values here. Let's see if that, I guess we should start it maybe with -e. Okay, let's see, come on. I mean, this is still not the solution of this challenge, but we would get a little bit closer. Let's see, I want to figure out how to maybe make this faster. Argument is not an integer. Model as long. Let's try that again. There's this set3 function simplify, so we could maybe simplify T1 and T2. Okay. I think this worked. Did it? No, wait, I'm confused. Wait, let me check. So we have shellcode here in the front. Then we add our sync block, and then this, and then, I mean, it might still be the wrong endianness. So this didn't quite work. Let's see if we turn the endianness here around, if this fixes it. I guess it didn't really speed it up. But wait, I'm confused. Wait. Ah, crap! I showed the wrong output. Oh, I'm stupid. Come on. Oh no, I'm an idiot. I'm still appending this code here at the end. Let's remove that again from our code stuff here. That was stupid. Okay. As long as we keep finding things to fix, I'm all okay. I worry when I don't know what I can fix. As long as I notice these small issues, I'm okay. When in doubt, change the endianness again. Where is my mistake? Let's always run, I guess, both endiannesses just in case. And not only that, we can also run M1, like turn these around as well. You know, desperate measures at this point. But I'm not smart enough to figure out what the deal is. While this is running, let's quickly think through this again. We run the shell code through our checksum, and we get out of there a T1 and a T2. We return T1 and T2, so this should be fine. The order T1, T2, and then we pass this to gen block. Gen block takes T1, T2, assigns it also to T1 and T2. This is a mistake. This T1 here was overwritten by this here. This T1, no, wait, stop, back. We write here a new T2 that is then used in here. And we are using here the original T2. This is obviously wrong. So this must look like this. This takes so long. Oh, I'm so nervous. Maybe at this point we should revert the code to the loop. And then this wouldn't have happened. Okay, so with this change, it takes much longer now. Still running. Okay, now I'm scared that this wasn't as easy. Uh-oh. Let's verify that everything is now correct. So T1 is used here. And then T2 is written. And then T2 is used here. And only then T1 is written again. It ran through. Okay, so this checksum is wrong. Wait, what are we looking for? ADC757, ADC7. This is wrong. This is wrong. This is the output. The first one. This one here. Let's try this with the 6060 shellcode, and then we test it. Okay, let's do this. But I have to pee. Come on. Come on. Come on, do it. Why does it take so long? Yeah! This output looks so good. Okay, let's try this. We need to basically get this output here. Print. Okay, wait, I deleted, obviously, now I deleted the sync block. Hexlify the shellcode plus the sync code, and then hexlify the code. And then we need this output basically also here at the end. Can't concatenate strings to bytes. There we go. Okay, so this should be our code now. So let's copy that. And then we go to our test here. So theoretically now, if we use this as our new puzzle, now obviously we don't create a contract. So the function itself should fail, but we should pass the checksum test. This is the important check, and we should pass that one. Okay, transaction pending. Got a revert. That was understandable. So we calculate the checksum here. Okay, so here's the require. Oh, no. Here's an AND. The checksum is EF6C, but why? This makes no sense. Wait, okay, wait, this makes no sense. Let's see, if we remove these 666, so if we just take this code here, is this still fine? Maybe because I added 2 bytes at the end. Please also fail. Please also fail. Uh-oh, the browser is hanging. Uh-oh. No! Fuck. Compile, deploy. So now we need the original code again. We have the Montagy and the P3. When we compiled that one, we take the P3 contract and copy its bytecode. And then we take this here. Okay, call register code. So we set the game to true. and new puzzle. Now with that call, so this is the call that should work. Okay, yeah, it finished. I didn't notice. Okay, so now what if I add 2 bytes at the end? Crap, this also succeeds. Oh no. Oh no. Oh no, it doesn't work. Okay, so let's make some sanity checks. So only shellcode. Then when we have that, we get the sync block. So let's try this again. Let's only take this here, this code for now. And then let's call new puzzle with that. And let's see what the checksum calculation is. CS is EF81, EF81, 5E10, DB2A, DB2A, F293. Okay, so from the first round, it's correct. We come to the same T1 and T2 value, but the sync block is now the important part. Was there anything else than T1 that like carries over into the next round? S is always reset. M are obviously always the next value, so they are not dependent on the previous stuff. It's just important that it's always aligned correctly. And then, so S is always set, and then P1 obviously are all set here. And T1 is from the initialized value. And as long our T1 and T2 are these values, it should work. Are these values correct? Let's check again. T1, T2. Oh, maybe the endianness of them. Do I need to maybe turn them around? No, that should be fine. We got the correct checksum calculation out. Okay, so earlier, this was our sync block. So let's see what happens if we get the same sync block again, and let's also test the calculation here. New puzzle. Okay, reverted as expected. And so CS here, this is weird. The sync block should theoretically get us these T values, but it doesn't. But it did work earlier. Like it got the correct checksum when we ran the shellcode with the sync block and the code. Am I still maybe fucking up the order, like M1, M2 and stuff? It's maybe reversed. I mean, M1, I take the last one, and so here I put M1 also at the end, so it should be fine. I guess for fun we could like rearrange them. Let's see what happens with this input. Wait, does this look better? It is reverted. 731. This is correct. Oh. Cancel that. So we need to change the order of these. Why though? This worked earlier. Okay, this will take a bit. I need to distract myself. Let's go on the worst website ever. Wait, I shouldn't waste my time on live stream fails, okay? I should be thinking about, if we have that, what can we do then? Because I have no damn clue. So this means we can call deploy. I need to research how this deploy or create opcode really works. So let me put this here on the side to keep an eye on it. And then research. When create opcode is executed, the EVM creates a call frame in the context of the new contract. Oh, it ran. It's done. So the final block doesn't look good. This should be a different. And then this output is also, let's see. Okay, wait. Let's look in my code again. So now it built the block. I print the shell. Oh, I didn't print the sync block though. Okay, so. And then this is the sync block. 6080, the 60. Ah, crap. No, it's like this completely reversed crap. 080. Okay. So up until here. Okay, this obviously fails. Let's check CS. So CS is now. Okay, wait. This is wrong again. Hey, I'm so confused. So this here created this here. Okay, this is ordered the other way around. Let's try this again. Now this creates the expected output. Okay, no, so this is the wrong order that I just did. This is wrong order. This needs to be this way. But let's also print the shellcode here. Okay, but if we know that this produces the correct thing, then theoretically, we should be able to append now this code here to it. Okay, let's try this whole thing again. I thought I tried this earlier, but maybe I didn't. So 0x, no wait, I had, this already had 0, okay. While this is running, let's execute the script also again. No, god damn it. Compile Montagy, copy the bytecode of P3, and then let's copy this code. Now please don't crash. Revert. Why? Wait, this looks pretty good. So this output, so this whole output produces this here. Let's check the actual code again. So this worked. Let's debug that. Oh, wait. Oh, the code is now, wait, the code is now different. Why? That's not the same checksum we had earlier. Wait, is this a different code? No, that's the same code. Why does it generate a different checksum now? Let's take this code again here. And let's call register. Let's register that code here. Try a new puzzle again with the same code. Oh, I'm an idiot. This was the wrong new puzzle code. Uh-oh. Can't make too many of these and then the browser crashes again. God damn it. Let's do this properly again from the start. First, we compile Montagy. Then we copy the P3 bytecode, which is this one here. So this is the P3 code. And then we go into here and we deploy Montagy. Then we take this P3 code and we register this code. Then we start the game. And now we take our sync block, which should be this one here. No, 1 by 2 much. It should be up until here, ending in a 4.6. And then we take that code and append it to that. And now this should new puzzle work. Okay, so this output, the code just finished, and this looks good. You see, this is the intended CS, and here's the shellcode plus sync code plus block has the same output. Okay, so this seems to work. But this failed again. Oh no, it's reverting in the contract create. That's good. Here, let's go back up. See the push 60? It does here the create and jumps to our code. Okay, yeah, it worked. Okay, so now we can deploy arbitrary contracts. We can use Z3 to calculate the checksum, blah, 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 blah. Yes, okay, awesome. Now we just don't know how to solve it yet. Okay, so now we just need to think about what kind of a tech contract we could deploy. So either when the contract is created, we call something on the contract and does something like the solve, for example, or during this create, during the init code, during the constructor code, we do stuff. Okay, so let's try this again. Let's take, I guess, let's make sure that this is the code that is also registered. So at the 6.0 here, because that's basically the code we target. So let's just make sure that it's registered. Okay, so let's try this from the output here again. This here, make sure this is registered because this is basically the code that we target here with the whole thing. So then I just did that. And now let's try. So let's try the whole thing. New puzzle. Now, please don't crash now for this simple test. Fuck, it didn't work. Anyway, it should work. We just like, I don't understand. Anyway, it should work. Like we just did the push thing. Why am I testing this again? Here again, I'm like running in circles because I'm like scared of the next step or something. Okay. Research. I wanted to research the. Yeah, I crashed again. Okay, so let's research the call. We can't call solve, but it gets transferred to the owner. This is so frustrating. Let me open this page in the VM. Okay, great. Now this browser is hanging. Oh, god damn it. Oh, the whole VM is hanging. Well, great. Okay. It would only work if the owner is actually our player address, but I doubt it. That wouldn't make any sense because then we could also just register new puzzles, right? I'm an idiot. Yeah, of course it can't be us. Because if it would be us, then we could also just register new code on the owner. I wonder what would happen if you do a delegate call out of a constructor. Now that should still work, and the context should still be the new contract though, except maybe that's kind of like a bug, a trick, because nobody does delegate calls in constructors, I believe. Let's read some stuff. Okay, so the page is loaded. Okay, so plugins. We want debug. Okay, let's debug that create again. So, crap. Okay, wait. Pile Montagy. Let's copy P3. Let's deploy Montagy. Let's register. Let's set the game to true. And now let's deploy that also as the new puzzle. And then I want to check the storage again. Okay, so when we start executing in here, we have here the solidity state, which is like here these mappings inside of this call stack. Storage completely loaded. Okay, so here we have these storage. Is this the owner? Yeah, this is the owner, storage key 0. Storage key 5 is a true. And this is the, I believe this is the checksum thingy. Let's go back. I want to be, in here. So here we are in the constructor. So here it still knows the owner, official checksum, winner info, game on, full storage changes, storage completely loaded, but this is not shown now inside of the other storage. And this is the server value in storage. I don't think we can do much here. It's still weird what the solve with the memory info does. Okay, I'm kind of running out of ideas at this point. But maybe it would be useful to review how the winning condition again is exactly checked. Maybe the winning condition is not that the money is sent to us, but just that the money is sent back to the owner. Maybe that is enough. Wait, once the balance of the target contract is equals 0. Oh, wait, then we can actually do it already. Wait. Oh, shit, I want my Docker output. God damn it. Stop hanging. Fuck. Give me my Ubuntu back. Fuck. Okay, so we have that running again. So we have our pwn code again. So basically what we want to do is we want to create a contract. So let me get my Accurata Monica test stuff again. Create logger contract with this data. All right. Okay. So this should be us. Basically, we want just this P3 contract here. So because then we can just easy solve this, call the easy function on there. So we just copy the bytecode of that. Create P3. We want to send this, and then we wait for the response. Okay, let's see if this works. So we sign this. P3 contract should then be this. Okay, P3, TX and here, and then we send on. Okay, so this needs a close. Okay, so let's, I guess, try this. Just to not get confused, we can comment out this stuff up here. tx is not a constructor. Oh, crap, this is like old code. Okay, we need to get this code into like, okay, so we can get Ethereum tx out of here. Send signed transaction is not a function. Okay, I need to install like other modern versions. This is like really irritating. Okay, so apparently now we finally have created this contract. And so next we want to call. So we deployed that contract, right? So we want to, I guess we can just here deploy p3 and then we call easy. This failed because it tries to call the server. That's fine. So we just want to get the input here, copy. So this should be the call. Nonce too low. Oops. Nonce is 0. Nonce is 1. Okay, nonce too low. So obviously we need nonce 1s and 2. We can later. So we created a new contract now, and now we called it, but status is false, was reverted. Oh no, we don't want to create this contract actually. I'm such an idiot. We want to take this code here. This is our contract initialization code. And actually we want to run this through our shellcode stuff here because we need the sync block. So let's print the sync block here. Okay, so now let's solve that. Okay, and while this is running, we can continue implementing the code. So we are calling now, yeah, let's get the output again here because we want to catch some stuff there. And let's comment that stuff out for a moment. Okay, so let's go back to the first, crap. Let's make if number smaller than 10. I don't think we need more than 10 blocks. Okay, so I think this runs too fast. We only get the blocks, but not the transactions are all null. Block 1. There are TX, but they are null. Why are they null? Let's see, get transaction. Okay, now this worked again. Awesome. Okay, so basically we want to get, okay, so here, probably creating the contract address. Okay, so here's the output, block 1 receive. Okay, then block 3, block 4, block 5, block 5. Here we have a TX in block 5. Okay, it's a bit out of order here. So here's the receipt, here's the actual input. So this is calling 81D83 stuff. Which function is that? We can quickly check here. So this must be the register call or something. So register code 81D0. Okay, so this is one of the codes that we could use, which is pretty long. I think the other one was maybe a bit smaller. Let's check the other one. So this one, yeah, this is the other register. Let's take this one. This one is shorter. Then we don't have to pay so much gas. By the way, our code finished. So this should be the sync block. So theoretically, we should take this code, our shell code, and the sync block. So that is the register puzzle data. All right. So now we should be able to create this transaction. And let's quickly check the output here again. I want the from address. So in the TX, we get a from. And do we also get it in the receive? Yeah, we also get a from. Okay, great. So I only want to print blocks. I guess we can comment out this. I guess we can show which block we are at. And then we only print if the TX from is equal to address from. We are calling here from the address from this is our data, register puzzle, and we call here the one contract. So we had here the contract output somewhere. I guess we have the contract address also in here. There we go. It's in block number 7. We sent that to here with register puzzle. So this should register our puzzle and then success. Let's see. I'm not sure if the gas limit is high enough though, but we will see. Is this here the issue? Nonce too low. Okay, yeah, makes sense. Nonce too low, so let's try nonce 3. Status false. Has been reverted. Gas used. Gas used. Maybe it was too expensive. Let's see. Nonce too low. So this is the valid code. Let's test this here locally again. Let's refresh. So we have here a clean slate. Okay, so we first compile Montagy, then we deploy it, then we set the game to 1. We register code, register code pending. While we are waiting, I can grab what I think should be the correct code. Okay, so it's ran. Let's first create a new puzzle from that, so we can also check the checksum stuff again. And then let's grab what we think our, hopefully this is not too large. And okay, so this worked. Now let's, our code. I need to change, change Chrome, change JavaScript, hang timeout. Maybe this code is already too long for the checksum calculation. Okay, no, so this worked. Let's maybe quickly make check here what the checksum was. So here's the S store. Okay, so here we have the XOR. So the result is our checksum. Okay, so this should be our checksum. Only this one. This should produce the same checksum. Oh, maybe I also screwed up the alignment. That could be an issue. Debug this code. XOR result. It's this one here. No, this should work. This should work. Did I copy now the correct code? Just make sure. Yeah, I did copy the correct stuff, right? So this should work. If this was really the correct deployment, let's check this again. So here's the TX of 1 with this input. And then we have the block 1 receipt, creates transaction hash, contract address. So this is our target contract. Let's make sure that this address is correct. We are sending to, yeah, so this is correct. Then we have block 3, block 4, block 5, block 5 TX, block 5 receipt, block 5 TX. Here we have this input call, but this is the long one. That's not the one I like. 7, block 8, block 7 TX. So this is the shorter one. So let's again make sure I copied the correct. It should be from here, yeah. So this is P2 code, and this is our P3 code. Our actual code that we sent is P3 plus sync plus P2 code. Okay, so this should theoretically work, but maybe it's really too large for a contract or something. No, that can't be. I don't know. There could be maybe some limitation that we run into. And if that's the case, then maybe we want to not generate, you know, like the intermediate block that then where we just append the real one to get the actual checksum, but actually just generate the proper checksum that we want in the end. I guess while we are testing here, I could run this again in the background to get this value as well. So that would be okay, so the sync block plus the shell code created. Okay, so this also ran through. So shell code plus the sync block gives us basically this T1 and this T2. So now we register just the P2 code. So let's check again. Here's the XOR. The result is 51C112ACF439C. Okay, so this should work. So theoretically, this here should be now our puzzle. Let's try this. So this is shorter. This should hopefully not crash now. Okay, so this worked. Try this again. Maybe this was just really too long. So so let's not use the P2 code and just, I guess we can directly go in here now. Okay, let's try this again. Go there up. Crap. Let's see if we can open Remix on here again. And then we can try to connect to Web3 provider, localhost, okay. 8545. Oh, I need to specify the RPC cross domain. This is a little bit annoying now. I guess we could like, so we could go in here, launch chain, RPC, RPC course domain. It has here a star. So theoretically, maybe this should work, but maybe not with this Firefox version. Sudo docker commit sudo docker images. Okay, so now we have here a second one, so we can, let's just kill this one on 2. So let's, insufficient gas. That's kind of weird. I guess because we didn't, okay, it didn't work. Okay, maybe we can make it work with such a shitty plugin. Unable to connect. Okay, then I guess whatever. Oh no, I'm an idiot. I sent the wrong thing. I need to basically copy this input here. Here, no, this one here? New puzzle. Yeah. Oh my god, I'm such stupid. Okay, so this should not work now. Okay, so this did something else. What happened now? None's too low. Oops. Okay, no. Okay, false alarm. Why did it not work? We created this new puzzle, right? Let's debug this further. So this bytecode here is definitely our P3 code. Okay, so new puzzle. Okay, so let's get the address of this contract. I mean, it should be then in last child address, right? So we should be able to read now last child address. So this should be now the P3 contract. Let's call Alice on it. So this worked and then did the transfer. And if we check now in Montagy, we should get winner info Alice. Okay, so this should work. I don't understand why it's not working. Let's try a different call, just to make sure this works. Like, let's just get something. We want the winner info anyway, right? So we can just call this. And so we can copy that input. Get winner info, and let's just like copy that out for a moment. Okay, get winner works to get. Okay, this is nice at least. Okay, so we can get the winner. Let's maybe get the game on value just to ensure that the game is running. The nonce. Okay, so input 135 and the receipt. What is this other TX with this input here? Wait, this looks wrong. Do I actually accidentally send some bullshit as well? From D05. Hey, wait, what? This is the test. This is my, Game on, data, game on. This is the test data. Wait. They just maybe take ages to complete. Status false. Okay, I don't know what happened there, but one important call for us is also last child address, because here we can see the last contract if we created one. Let's see, can we debug this? 3.backtrace add. Okay, so we have the full 51 megabyte trace. Let's look at the debug trace. Okay, so I don't know. So I don't know what the fuck is going wrong. So I'm using now the debug endpoint to trace the execution of the transaction. It's a very detailed trace and it's huge, obviously. So I executed that and now I have the execution trace in a JSON file. And so I guess now we just need to look at that. Let's see, it's a huge JSON file. I guess we write some Python code. Oh no. Opening that 50 megabyte file, is that too much to ask? Are you kidding me? I do this only for stupid videos. It's so frustrating. I wish I would not have to work in a VM, but my recording setup is just like that. Okay, so window crashed, fine. Come on, I gave you 8 gigabytes of RAM now. Oh, gosh, I'm so mad. Okay, so now we have the trace, and I immediately recognize this. So this is the XOR in the calculation of the checksum calculation, and then it basically then does like store, load, and then it runs very quickly into the revert. So I assume that the checksum was wrong. Now, what we could do is we could print the stack after the XOR. So when the PC is this, and then we could look at the top of the, this is memory stack. Okay, maybe the swap was already executed. I don't know, let's check. Is this maybe always the stack after the instruction was executed? Or it's maybe down here. I don't know what the order was. Let's see. Oh yeah, okay, so down here, so this is the, okay, let's remember this for a moment. So now let's use this trace to check the checksum of the call that we were looking at. Okay, we need the transaction from the original thingy there. So let's actually just copy this into a new script. And then here we call recursively the block again. I guess we don't need that many. We can stop at the 10th block. So node. And so now we look for the targeted. Is this the one we target? This one looks shorter, yeah. So it must be this one here. So it would have this transaction. The problem is just that the history of the debug server doesn't go this far back. So if we do the curl, oh, it maybe does. It downloaded 41 megabytes. Okay, so let's check this out. Trace 2.json. And so here we have a different one. Okay, but let's quickly compare again with this output here. So why does this create an FD? Is this not what we wanted? But I mean, it doesn't matter. We can just like, now that we know the actual value, I can run my Python script again, right? So we know that this is the final state that we want. So where did I put this? So this is the goal that we want. So T1 is the one that goes at the front. So actually we want again block here. Let's just print the sync block after we've generated it. Okay, and let's that run again. And while this is running, let's test this again. So, and while this runs again, we do the same thing again, register code. And then let's debug this. We go back up to where the XOR is. Okay, so there, XOR. Let's check the stack. It's 5100 here. Okay, I seem to just like take the wrong part of it or so for the generation. I don't know exactly what I screw up because it should be this one here, but it doesn't matter. If we get our output, we should be able to, we should have the correct sync block to place at the end of our code. Maybe the reason for that is there are a lot of null bytes at the end, which maybe are actually cut off because I believe the original code was something like this maybe. Okay, so let's debug that. Or check the stack. Now it's FD3. Now it's the correct one. Okay, yeah, so this means we just kind of submitted the, well, anyway, if this code now completes, okay, it did complete, so let's check the sync block. This is a long sync block. Wait, what did I print here? Oh, I didn't generate the sync block yet. I'm an idiot. Okay, wait, but we can fix also in general my code because we want P2 code. We just need to remove these null bytes here at the end. And then this should be all correct now. Yeah, I changed also the code, obviously, so we don't append the code anymore at the end. We just want shell code plus sync block. There we go. Okay, let's run this again. Okay, right now. Okay, now the problem is that it does need maybe like one null byte or so. Just not too many. Just enough. Okay, we just need to make sure to later remove that again. Come on. Okay, now it's FD30, FD30. Okay, so this is what we wanted. So we can now take our, so this should be now correct. Input copy. Okay, let's try this again. Nonce too low. Okay. Success true. Okay. So now, did we see anything in the output here? Submitted transaction, recipient. Okay, wait, now we deployed it, right? So now we need the address of the deployed contract. Can we get that from the trace now? So we want the trace. Okay, let's do this. Let's do this again, pwn. Let's also remove this here. Okay, so we have the success true. We don't get the contract address, but now we should be able to call last child. So we should be able to call this now inside of here. So once we have that, we call get child and we output. Shit, we can't easily get that right. I need to write other Web3 code. Okay, I need to pee really quick. Let's write proper Web3 code. Contract ABI. So let's, from the compilation, we copy the ABI. Okay, how can we call now? Methods. And then we call owner, I guess, just as a test. Dot call from. Okay, so this worked. New puzzle. With the parameters of P code, I guess. And then we call that register code. No, a new puzzle should return the address. So that seems like it's doing that. So now we have the address here. So we can now create P3 of this address here. And now we just need the P3 ABI, which we can also get from the compilation here. Copy. And then .methods .easy and call that So did this work now? Am I registering here new? It seems too fast. Okay, so but theoretically we should now be able to also call last child address. I'm really confused by these results. That they don't make much sense to me. Maybe I should try send instead of call. Gas is missing, okay. From address from gas, let's use maybe what I had also in here. It's like this value. And then we replace. Okay, these arrows are a bit crazy, so let's try. This contract doesn't have address set yet. Please set an address first. P3. Oh, receipt P3. Okay, wait. Log receipt. Okay, now we get that out. And status true. Okay. So new puzzle should have worked. So we should be able to now call sending flag. It should work. Sending flag. Okay, I've now written up everything here into a gist. So I have here the pwn.js file that hopefully does all the magic. Then I have here a quick setup to tell my teammates that they have to use Node and then npm install the correct versions and then simply run the pwn script. And afterwards, they should run the trace script, which should hopefully output everything, including then the flag in the end. And I just noticed, that's why, I just went over there and wrote furiously because I just noticed that this is obviously localhost. They still have to replace it with the challenge server. So yeah, I basically quickly send it to them and hope that it just works. So while they do that, I just want to quickly try it again. So I'm gonna, because the sending the flag didn't work because it was insufficient funds. So I wonder if I maybe reset everything, start from fresh if it then works. So let's stop that container. Okay, so it stopped. So let's start the server again. It's running. Let's wait until, make sure block 5. Let's wait until block 15 or so. Then hopefully it should everything be set up. It's still doing stuff, so let's wait a bit longer. Watching balances target. Okay, so now it's waiting. So let's execute pwn2. Status true, should have worked. Okay, sending flag. Okay, yeah, it should work. It should work. Oh my gosh, it should work. Oh my gosh, please work. Okay, so here on the laptop, I have Signal open and I'm communicating with one of my teammates right now. Oh my gosh, please work. Please work. Ah, crap. I have to put stuff in the fridge. Okay, my teammate hasn't responded yet. Oh gosh, I'm so nervous. My teammate just wrote me it's currently running, and running probably means that it's executing the trace, which means that maybe the pwn was already successful, but I don't know yet. So I asked if he can send me the output from pwn.js, because it should look something like this status true here is very important. Okay, the output they sent me looks really good. Yeah, we got it. Okay, sorry, I needed to do this quickly just off camera. So he just sent me this output here of the blocks because he wasn't sure where the flag is. And so I scrolled down, and the other output that he had was that here, these were the pwn.js instructions. And then afterwards, here in block 17, this is when the flag was sent. And you can see here, this looks like ASCII. So let's just take that, decoding that as hex. There it is. Real World CTF. Code is cheap. Show me the opcode. Oh, and 1 cup of tea, please. There we go. I solved the challenge. Can you believe it? Oh, man. Okay. It's now 2:20 a.m. in Berlin. So basically, the CTF has been running now for 24 hours. In China, it's just early in the morning. Like, the team basically just appeared in the venue a couple of minutes ago. And so, yeah, nice. And I'm pretty tired. I will ask them if I can help out somewhere, maybe with some of the web challenges, maybe have a look. But other than that, I don't think I will stay up for much longer anymore. So I would say this challenge was so much easier than last year. The blockchain challenge from last year was just insane. The blockchain challenge from last year was really about Ethereum internals. And back then, the author already said that it's the hardest challenge he could come up with. And I do think that this is probably as hard as it gets for an Ethereum challenge, if there are not other like obscure bugs involved that like are kind of like ODays or weird quirks that haven't been publicly discovered yet. And so this challenge was less about Ethereum internals. It was basically in the end just like a crypto challenge, like reversing that checksum. Basically in the end it was just Z3. Now I think I could have gotten to that much earlier if I didn't miss this small detail. For the whole time I for some reason thought that I need to steal the money, transfer the ether to me. But it took me like so long to realize that the challenge description said it's just sending the ether away. It doesn't mean that you get the ether. So it was totally okay that the ether goes back to the owner. Oh my gosh. But yeah, anyway, I'm still so happy that I solved it in the end. Not too big of a failure, I guess. I hope I made up for failing this last year. And I hope you see that it takes a long time playing CTF challenges like this. I probably worked on it actively, ignoring the breaks for maybe 10 hours or so now. And I'm just a single person, right? And the CTF has multiple challenges. So yeah, you need a team to solve this stuff. So I guess that was Real World CTF for me. Thanks for hanging out with me and going through the ups and downs of solving a CTF challenge. If you made it to the end of this video, you have a problem, I guess. Why did you do that? I cannot imagine anything more boring. I mean, I did edit it for somebody to watch it, so thank you.